Welcome you all for the second session of uh, the bandpass equivalent to low pass signals. Under this, the next topic is pre-envelopes. So, what is pre-envelopes? So, and how it can be extracted. That is what the pre-envelope of the signal is g cap of t. G cap of t, that is g plus of t is equal to g of t plus j times g cap of t. So now, what is G plus of t? That is only the positive envelope, that is positive envelope the signal. How it can be extracted? So it can be extracted when you are going to add that is G of t with the imaginary of, that is the complex term of the Hilbert transform G cap of t, then you are going to retrieve the pre-envelope signal. That is what in the expansion, that is Hilbert transform is defined as both the positive and negative frequencies. So the basic operation, the basic question is how we can modify the frequency content of real valued signal G of t such that the negative frequency content are completely eliminated. Negative frequency contents are completely eliminated. Either you go for selecting the positive envelope or else the negative envelope. So how it can be completely eliminated? By taking the complex of, that is the J term is nothing but the complex term of Hilbert transform. When it is getting added with the G of t, then it can be eliminate the negative amplitude, negative envelope of the signal. So for that reason, when you are going to take the frequency in terms of Fourier transform, so you are finding that is g plus of t, it becomes a g capital G cap plus of f is the cap is not there here. So g plus of f is equal to g of f. In place of g of t, it is g of f. So now plus j in terms of g cap of t, it is g of f, g cap of f. So what is g cap of f? G cap of f is supposed to substitute. What is g cap of f is equal to minus j signum of f minus j signum of f, okay, into g of f. That is what you are substituting in place of g cap of f. So we can rewrite this equation as in terms of Fourier transform as g cap of f. So g cap of f is equal to g of f plus j times g cap of f. G cap of f. This is the equation. G of f is equal to plus uh, here the value is minus j, sorry, plus, so here it is plus g of f plus j times g cap of f. So in place of g cap of f, we substitute the value of minus j signum of f into g of f. So now after multiplying this plus j and minus j, this becomes plus, and g of f is equal to g, what is that, g plus of f is equal to g of f plus signum of f into g of. So what is the g plus of f? So g plus of f is equal to 2g g of f in case of f is greater than 0. So now substituting the signum of value of 1. When what is the signum of f? I write aside here. What is the signum of f? Signum of f is equal to, so what is the functionality? That is 1 for f is greater than 0. Okay, 0 for f is equal to 0, and minus 1 for f is greater less than 0. So f is less than 0. This is what the signum function. After substituting this signum function, what is this becomes? So first function g of f written as it is. For the f is greater than 0, g of f is written as it is. This 1 is instead of signum function, it is 1. Now g of f, what is the value? Now 2g of f when f is greater than 0. When f is equal to 0, the value is 0. That is, in place of f, it will become 0 when f is equal to 0. And f is equal to minus, f is equal to 0 when f is less than 0. So here when f is less than 0, it becomes g of f minus of g of f. The value is 0. Okay. So because of that reason, it is going to have 0 value. Now, what is the magnitude spectrum of it? It is not 0. Okay, so here you can observe that when f is equal to 0, that is what in place of vf it is taken as 0. What is g of f becomes g of 0. Okay, g of 0. Okay, so this is what the low pass representation spectrum. So this can be a pre-envelope, that is what g of t. G of t can be taken the pre-envelope, that is 2 into g of f, when f is equal to only we have considered the positive envelope after passing through the only considering the pre-envelope. The signal g of t has no frequency content for all negative frequencies as illustrated in the figure. So this is what it is going to eliminate the negative frequency. It is going to retain the positive, but the magnitude is going to be twice. The magnitude is going to have twice of the signal g of t, g of f. So now what is the how it can be represented with respect to the time domain and the frequency domain. So that is time domain procedure. For a given g of t, first compute the Hilbert transform of g cap of t, then the pre-envelope of g plus of t is obtained by the equation 1. Okay, so that is what earlier I have shown you. So the frequency domain procedure, for a given g of t, first compute the g of f, then Fourier transform of pre-envelope of g cap of f is obtained by using the equation 2, and finally evaluate inverse transform of g cap of f. So now what is g of t? G of t becomes, in terms of time domain, that is 2 times 2 into 0 to infinity, because we need to consider only the positive side. G of f into e to the power of minus j 2 pi f t into df. So what is in case of negative signal, that is g minus of t is equal to g of t minus j g cap of t. Okay, so g cap of f, g minus of f, g minus of f into cap does not exist. G minus of f is equal to g of f into minus j and minus j signum of f into g of f. The value become g of f minus signum of f into g of f. So g minus of f, g minus of f is equal to 0, f is greater than 0. G of 0 is equal to when f is equal to 0, 2 into g of f. For the negative frequency it becomes twice the magnitude. So for f is less than 0. Okay. So this is an exam and how the positive signal and the negative signal are related. That is g minus of t is equal to conjugate of g plus of t. Conjugate of g plus of t. So this is an example how to convert the low pass signal into a take the pre-envelope. So when you consider only the positive envelope, it becomes g 2g of f at the positive frequency. It becomes plus 2g of f at the negative side. It becomes for the negative frequency. So this is what the pre-envelope for the low pass signal. Next, so now the representation is we got extracted the pre-envelope. Now use the application of that pre-envelope. The first what we learned, the Hilbert transform we are using to extract the pre-envelope, and the second topic is the pre-envelope, where you are going to extract, using that pre-envelope where you are going to extract the complex envelope of the bandpass signals. So this is what the expression it is, s plus of t, that is what the positive envelope, s plus of t is equal to s tilde of t e to the power of minus j 2 pi f c t. That tilde only represent the complex envelope. This can be represented in some terms of symbolic representation, tilde or transpose. Both are similar parameters. S plus of t is equal to s cap of t e to the power of j 2 pi f c t. Now s of t is the complex envelope of the bandpass signal s of t, and it is going to have, this can also be written as in terms of complex envelope signal. So that is s transpose of t is equal to s transpose of t is equal to s plus of t, and now the term becomes minus e to the power of complex exponential becomes minus e to the power of minus j 2 pi fct, minus j 2 pi fct. Okay, so this is the figure is going to represent how to extract the complex envelope of the signal. This is actually the signal s of t. It is in terms of taking the Fourier transform. Taking the Fourier transform, it becomes s of f. So this is s of t. Taking the Fourier transform, it becomes s of f. Now, see, this is the bandpass signal, which is going to have the two band of signals, that is for the low when a positive frequency and the negative frequency, having the bandwidth of 2 omega. 2W. Okay, so first when you are going to extract, only consider the pre-envelope. So this is going to be the pre-envelope of bandpass signal. Considering then it becomes a twice in the magnitude. So what is the spectrum of it? Fc minus W, only considering the positive frequency, and here it becomes FCW. So now when you are going to shift to the towards left hand side, so that is what the shifting of pre-envelope signal towards its left become the complex exponential negative, earlier what I have shown. So now the signal becomes equivalent to low pass. Now minus W0 to plus W. Now the signal which is going to have the magnitude, but it is represented in terms of low pass signal. Okay, so this is what this bandpass signal can also be represented using the canonical representation. That is total. That is what so far we have not considered any imaginary terms. Only we have considered the real term of the signal. So what is S plus of t? S plus of t is equal to S of t plus j into S cap of t. So what S of t is going to be considered? Only the real part of S plus of t. So when you are going to consider only the real part, it is S cap of e to the power of j2 pi f ct. So what is the complex exponential of the S of t? That is S tilde of t is equal to Si of t plus Sj Sq of t, where Si of t and Sq of t both the real valued low pass functions. So S of t is equal to, so the real, only you need to consider a real value. Substitute this equation in the equation 1, that is Si of t plus j Sq of t. In place of complex exponential, you substitute it as cos 2 pi f ct plus j sin 2 pi f ct. Now what is S of t? S of t now becomes, after multiplying these parameters, so considering only the real terms, so S of t is equal to Si of t plus cos 2 pi into cos 2 pi f ct minus Sq of t into sin 2 pi f ct. Okay. So next, this is what the representation of Si of t plus S minus Sj of t. So this is the magnitude spectrum. So which is going to have the vector having the magnitude root square of Si square plus Sq square and the angle of tan inverse Sq by S1. And this is for the complex exponential. When you are going to, the angles are getting added and magnitudes are getting multiplied. So this is the representation of bandpass signal in terms of complex envelope. So this can also be represented using the block diagram notation. So S of t is given and it is multiplied with the cos 2 pi f ct with this and the sin 2 pi f ct, and when you are going to passing through a low pass filter, you are getting it as the Si of t, and here also when you are going to passing through the low pass filter, only you are going to retrieving it as the Sq of t. So the below figure shows the bandpass signal S of t in phase and the quadrature components Si and Sq of t can be referred as synthesizer. Now we have to retrieve S of t. How? So we have to take the S of t, Si of t and Sq of t, that is multiplied with cos 2 pi f ct and sin 2 pi f ct. So one side it is getting added, that is what in phase function. The quadrature function is getting subtracted and you can retrieve S of t. So this is called the synthesizer. Earlier what I have told, it is going to be a analyzer because you are retrieving two low pass signals, that is Si of t and Sq of t. So this is what the polar representation of bandpass signal. So earlier it is the Cartesian form. Now we are representing the complex envelope signal in terms of polar form. That is S tilde of t is equal to A of t into e to the power of j pi of t, and where A of t and pi of t are both are real valued low pass signals. So based on the polar representation, the original bandpass signal S of t is defined as, that is S of t is equal to A of t into cos 2 pi f ct plus phi of t. So when you are going to consider the pi of t, that is what A of t is the natural envelope, simply an envelope of the bandpass signal of S of t, and phi of t is the phase angle. So what is the relationship? A of t is equal to Si square Si square of t and S square q of t. And what is the angle? Angle is tan inverse of Sq of t divided by S1 of t. What is S1 of t? Si of t. So Si of t is equal to A of t into cos phi, and Sq of t is equal to A of t into sin phi. That is what in place of e to the power of j phi of t, you substitute it as cos phi of t plus j phi of t. So considering those parameters, so the real value become a of t into cos pi of t, and the imaginary quadrature component become a of t into sin pi of t. Okay, so I'm going to end the session. So the next session I'm going to start with uh, band pass system. So how the complex signals are represented using the band pass system. Thank you for attending the session.